Hello, so thank you for watching this video. So today, we talk about estimation. So estimations like we have populations something like mu or sigma okay, mu population average, population standard deviation, or more general for this population we have an unknown parameters. So we denote this like in general we say we want to estimate this theta for a population. So how to estimate? So we have data, right? So take a sample. So we have data. Okay. So from data, so estimate. So the question is how to estimate. So we discussed it for population's average, the mu population average. So we use samples average x bar to estimate this mu, right? But this is like a common sense, like for estimate population average, we use samples average. But let's consider general situation. We have populations unknown parameter like theta. We how can we estimate this parameter theta from data? So for example, mm, we we know population follows this distribution, like x can be 1 to 3, okay? But the probability for each one is related to an unknown variable or unknown parameters. We call like this is like 1 minus theta, or here the half theta, half theta, right? So this theta is certainly less than 1, larger than 0. So this is distribution. So we don't know the theta. Okay. Okay. So then we take a sample. So suppose like we have this population. Population is 1, could be 1, could be 2, could be 3, like only those 3 numbers. This population, so take a sample. So suppose we take a sample like data is we have 2, 3, we have let's say 4 ones and 2, let's say 2 2, then 3 3 3 3. Suppose data like that. We have 10 numbers. Data is like that. So then how to estimate the theta? So question is how to estimate the theta. From data. So so how to estimate? So usually we have 2 ways. So answer is we have 2 ways. You should have 2 ways. One is called moment estimation. Moment estimation, ME. The other one called MLE. So MLE means, so here ME means moment estimate. Moment estimate. Okay. So MLE means M is maximum. Maximum. So L means likelihood. Like estimation. Okay. So what is the meanings? For M is just like for m is we use samples moment, like we denote as mu k hat, estimate populations, let estimate as mu k. Okay, mu k hat to estimate as mu k. So this moment estimation. So for MLE meanings like from the data, data like here take one, take two. So take one probability is probability is 1 minus theta. So here 1 minus theta happen 4 times. And 2 is half theta happen twice. Right? So 3x equals 3. We say probability is half theta, so half theta happen 4 times. So actually, like this, let's say, this is actually not so good because if they're probably the same, 0.5. Oh, okay. Probably the same is okay. Yeah. Okay. So we have like this. Let's say, so we can have this. We call it a probability function. Like we say 1 is 1 minus theta, right? 1 minus theta, 1 minus theta, 1 minus theta 4 times. And then half theta, this is 2 happen twice, right? And 3 take 3 half theta happen 4 times. So we denote this function as likelihood function. We denote this as f theta. So MLE means like we want to find theta such that this maximize the value. Okay, so we know this 1 over theta, those things for means probability. So we just say find theta that make this probability the highest. So we can say that this is most likely, right? So maximize the likelihood estimate. Okay. So now let's use these 2 methods to estimate the theta based on this data. Okay. So for moment estimation, so at the first we found, let's say, find a population's moment. Oh, we say this is, let's say, but anyway, this is we say mu1. Mu1 equal ex, right? So ex equal like x1 take probability 1 minus theta, right? Plus 2 times half theta plus x can be 3 multiply probability, so a half theta, right? So we find mu1 equal that's 1 minus theta plus theta plus 3 over 2 theta, right? Okay, so this equal 1 plus 2 over 3 plus 3 over 2 theta, right? So this is the population's first moment. So then let's say what is mu1 hat? So this is the average from the data. So let's say we have 10 number. So here we have 1 plus 1, just like that, right? Plus 1 plus 1 plus 2 plus 2 plus 3 plus 3. Okay. So this is a samples moment, first moment. right? Okay, so we find this number equal, this is 4 plus 4, 8, 8 plus 12, 20, right? Okay, so this equal 2. Okay, so we just let use this 2 to equal this 1 plus 3 over 2 theta. Okay, so we get this theta equal 2 over 3, right? Just solve this theta. So this is not a true theta. We say this is theta hat, estimated theta. Okay, so this is the moment estimate. So here we just use one first moment we get the estimate, so we are done. So sometimes if we need a second moment or third moment, so here by the way, so we say mu like mu2 hat. What is mu2 hat? Mu2 hat is just equal x1 square plus x2 square plus xn square over a. Right? So mu1 hat is x1 plus x2 plus xn divided by a. Mu2 hat is x1 square plus x2 square plus xn square. So hat divided by a. So mu3 hat is just x1 3 plus xn 3. Right? So this is sample moment. Sample moments. Okay. Okay. So then let's say, so what is MLE? What is MLE? So MLE is we let's say what is likelihood function. So f theta, we remember this is equal like 1 plus 1 minus theta. This is 1. This is probability for 1 appear. This 1 appear 4 times, and 2 probability of 2 appear 2 is half. So this is half theta happen twice, and 3. So 3 appear probability. We take 3 is also half theta, right? So this happen 4 times. So we want to regard this function about theta. So we just find the maximum value of theta. Okay, so this we simplify a little bit. 1 minus theta 4. So here we can say, oh, they're the same. So half theta 4 or half theta 6. Right? So maximize that. So we use derivative, right? Let the derivative equal 0. So and because it's a product form, so we also can consider thus like ln f theta. Let's say if theta is big, saying this ln log f theta is also big. So but for log, so we say this is L function. Okay, L theta. So this equal 4 log 1 minus theta, so plus 6. So 6 log half theta, right? Okay. Okay. So we just let the derivative equal 0. So this actually we regard this is a function of theta. So this equal 4 1 log derivative 1. Let's say this, remember this log x derivative equal 1 over x, right? Okay, so we use this. And here the 1 minus x also need to multiply, need inside the derivative. We say this is a chain rule. So this is 1 minus theta derivative should be -1, right? So plus 6. Okay. So here half theta. 1 over theta, we got half. Then also multiply half theta derivative, so half. Okay. So we can say this equal the negative 4 1 minus theta. So here, let's say half, I can just cancel, so this equal plus 6 theta. So we let this equal 0. So we just try to solve this equation. Okay, so let's say 4, so 1 minus theta equal 6 theta. Okay, so this equal, let's say we can simplify, let's say 4 equal 6 theta plus 3 by now, but it becomes 3 1 minus theta, right? Okay, so this equation, so let's say the become polynomial equation. So 3, so we just change this to standard form, 3 theta square minus 3 theta plus 2 equals 0. Okay, so solve this theta. So let's say, can we use factoring? Let's say 1 3 1 2 2 1 1 2 2 1. We cannot. Let's say, what is the solution? We cannot use factoring. Right? Negative 2. Yeah. Okay. So for this one, we cannot use this. So this one we have to use formula theta equal. Maybe I made a mistake somewhere, so I need to check it. Yeah. Okay. Oh, I made a mistake. Yeah, I made a mistake. Okay, so this is actually not 6 theta, 6 over theta. Yeah. Okay. Oh, I made a mistake. 6 over theta. So, okay, so this is mistake. Okay. So then solve this. We say 4 theta equal 6 1 minus theta. Right? We can say the let's say, so here 10 theta equals 6. Okay, so theta equals 6 over 10. Oh, 6 theta equal 3 over 5. Okay, so we denote this as theta hat. Okay, so this is we use 2 methods to get to the estimation for this parameter theta. So for this simple examples, we usually the 2 estimators should be the same by the 2 methods. Yeah, no, this is 2 over 3, but this is 3 over 5. Oh, different answer. Yeah. Okay, but anyway, so this is a typical simple example to show you there's two methods. Okay, moment generating function. No. M is moment estimator, and ML. Okay, so this is discrete situation. So let's consider a general continuous situation. So let's consider just like a normal distribution. So let's say like X, we say population follows normal. Mean is sigma, mean is mu, standard deviation sigma. So from this population, we get a sample, we get a data. So data, so we have like this, like x1, x2, we have those numbers like xa. So from the data, find estimate, find estimate for mu, estimate for mu hat, or estimate for sigma hat. So here we also have two methods, right? We say by this method, by ME. So by ME, we try to find mu, the mu hat, and sigma hat. And by MLE, okay. So now let's consider this problem. Let's check up M. M by M is moment estimate. So so at the first we know moment estimate. This mu is just x is like mu1, just the mu, right? Okay. So then what is x bar? So we say like let's say mu1 hat is just the x bar, just equal x1 plus xn over x, just x bar, right? Okay. So we just use x bar. Let x bar to estimate mu1, right? Estimate is mu. So for sigma square variance, so at the first we have this formula like variance. What is the variance? Equal, according to definition, is x minus mu square. So we have this formula equal e x2 minus e x square, or in terms of mu1, mu2. So this is just mu2 minus mu1 square. Okay. So here, so for estimate the sigma square, we use this. So we say like, okay, variance sigma square's estimate, so equal, we say equal mu2 hat minus mu1 hat square. Okay, so what is mu2 hat? Mu2 hat equals this. Equal mu2 hat equal just equal x1 square plus x2 square plus xn square over n. This is mu2. And mu1 hat is just x bar, so x bar square, right? Okay, so we just use this to estimate variance. We estimated the sigma 2 square. So standard deviation sigma, it just take a square root. Okay, so here we can simplify a little bit. I may rewrite this estimate, like do some math. So we say minus n squared become like we put n denominator. So this is just n x1 square plus x2 square plus xn square minus n x bar square, right? So we put minus x bar square as x1 square minus x bar square, or plus x2 square minus x bar square. So we can say this is summation for xi minus x bar, or xi square minus x bar square, right? Yeah. So x1 square minus x bar square plus x2 square minus x bar square, right? Okay, so here we also use a little bit algebra. We say summation xi square minus x bar square equal xi minus x bar square. We have this. So why we just expand this right side? So this equal actual summation like xi square, right, minus 2xi x bar plus x bar square, right? Okay, so this summation equal, so here summation xi square. For this one, so this equal to summation like for this like summation 2x bar xi. Oh, we put xi first. So here summation xi, so x bar is constant, right? So we can write this like this. Then plus we can put this as n x bar square. Okay, so this equal xi square minus 2. So what is the summation x bar? Summation x bar is n x bar, right? Let's say like here a little bit algebra summation x equal n x bar. Okay, so this become n x bar, so multiply x bar, so x bar square plus n x bar square. Okay, so we find this equal summation xi square minus n x bar square, right? So this just equal summation xi square minus x bar square. Okay. Okay, so we just simplify this as so we can have this. We say so sigma squares estimate equals this, equal summation xi minus x bar square over n. Okay, so here is from moment estimate, we get this estimate for samples. We use this formula to estimate the population's values. Okay, so now let's consider MLE. So how about MLE? So MLE, so we have those data is x1, x2, like we say. We have those data. So how about MLE? MLE, so we have data like this. Data is x1, x2, x2, xn. So what is the likelihood function? So likelihood function related to mu and sigma. So likelihood function is just the probability, like looks like a probability to take x1, x2, and xa, right? Just like a discrete situation. So we can denote this as here. Okay. Here we have some notation confusion. We say this is not a function. This is just a function, likely function. Okay, likely function. So here we say the probability for take those xi. So we just multiply together. So here fx is probability function. Or in continuous situation, so this is density function. In discrete situation, just probability for taking those values. Okay. And in continuous situation, so this is fx density function. So for density function, we know for normal distribution, density function is thus like radical 2 pi sigma. So e negative 2 sigma square. And so here x minus mu square, right? So this is the formula. But here by now x take xi. Okay? So this function is just like that. Okay. So this multiplication, we say this equal radical 2 pi n's power and sigma n. And so this multiply this power will become addition, right? Become so we also can denote it as xp means but the xp or right? Let me see. Sometimes we use this xpx, right? So this function is just equal this function x. So here we still use e. Okay, so negative 2 sigma square 1. So here become like a summation xi minus mu square I equal 1 to a. Right? Okay, so then so here x1, x2, xn are given data. So are fixed number. So only unknown variables as mu and sigma. So okay, so this is likelihood function. So we need to find mu and sigma that maximize this product. Okay, so we just take a log. So let's say we still denote this as L function of mu sigma. So equal log this. Log. So in math, log, ln same. Sometimes we like the ln to indicate this is natural log. Sometimes we just put the log also for natural log. So log for this. So log this, so we just log for each one, right? So this first one, log for this term. First one n log this. So this equal like this negative half the power. But anyway, here half the power is 2 pi. So here put half, right? And here negative 1. Okay? So first one take log this. Then here minus n log sigma, right? And so this one will become like a minus 2 sigma square. This summation xi minus mu square. Okay, so we want to find mu sigma that makes this number make this derivative equal 0. Okay, so here we have two variables. So we should use like a partial derivative, right? We have two variables, so partial L over partial mu. This equal. So here we use derivative about mu. So here sigma we regard as constant. So this first one, the constant, the derivative is 0. The second one is this equals 0. So this equal negative 2 sigma square 1. This is constant. So this is derivative. So this is summation, the derivative of summation. So here we say This is derivative xi minus mu derivative. So here we the derivative is about mu. Yeah. So but anyway, so here we have this square derivative is 2, right? 2xi minus mu. Then we also need to multiply -1, right? Yeah, because xi minus mu. So here mu is a variable, xi is constant. Okay. So we just let this equal 0. Okay. So we find this. There's a constant. There's a constant. Just so we get the summation xi minus mu. This not infinite a. This equals 0. So what is mu? So we can get the summation xi minus in mu. So let's see. We expand the summation xi I equal 1 to a. So minus summation mu. So I equal 1, summation mu means we have mu plus mu in mu equals 0. So we get mu hat equal just summation xi over n. So this is just x bar, right? Okay. So from MLE we get the same estimate for mu. So just the just the samples average. Right? Okay. So for sigma, so we say partial L over partial. We can regard so here partial sigma. We just let this equal 0. So what is this derivative? Okay. What is this derivative? So let's check this likelihood function first. This one. So first one derivative equals 0. Then n log sigma derivative n log sigma. Maybe I should write it down here. So that's equal negative n log sigma derivative. Okay, and minus this part of the derivative 2 sigma square summation xi minus mu u square. Yeah. So there's a derivative. Yeah, I equal 1 to a. So we also use there's a derivative. But remember, the derivative is about sigma. Yeah, so here also sigma. Okay. So we find this first log derivative is 1 over sigma, 1 over x, right? So that's equal negative n 1 over sigma. Okay. And for second one, so this is just the summation. This summation constant. Okay, so we can take the constant outside. Half is also constant. Half summation xi minus mu square. So that's constant. Okay, so only use derivatives just this 1 over sigma square derivative, right? That's derivative. So just 1 over x square derivative. So this we also can just like this use this formula, just like x negative 2 derivative. So x negative 2 derivative equal negative 2, then x negative 3, right? So this is just equal, okay. So this derivative is just equal negative 2 and sigma negative 3, or we just say sigma 3. Okay, so we let this equal 0. Okay, so we solve this equation. We solve this equation, so sigma. Okay, so we simplify a little bit. So this equal to negative n over sigma. So here become plus half cancelled. So this summation sigma 3, right? So equals 0. So cancel 1 sigma. So we find cancel 1 sigma negative sigma n plus okay. So we get sigma squares equals thus summation xi minus mu square over n. So mu, we already get the estimate. Mu is x bar, right? So we have get so finally we say sigma squares hat equal n, so here summation xi minus x bar square. Okay. So by these two methods, we get the same answer. Now estimated the population variance like this. So use the two methods, we got this. And same, right? Two methods, we got the same answer. So here let's see. Yeah, we already have this sigma squared equals this, right? Okay. Okay, but we remember for samples variance formula, for samples variance, the formula is thus: a square samples variance equal summation xi minus x bar square I from 1 to n. So here divided by n minus 1, right? The formula like this. So here we say from ME, MLE, we get the same answer. So should divide by n. But we say our formula samples variance is this divided by n minus 1. So this so we claim this is square samples variance. So we just use samples variance to estimate population variance. So we claim this, right? A square is the best estimate for populations for variance. So we explain what the best meanings. Best meanings MV, let's say MUV, no, MVU is best. I remember MVU. Oh, I got confused. MUV no, I got confused. M means minimum, so MV, minimum variance. So use unbiased estimate. Okay. So like we said, we proof compare this sigma square hat is this divided by n or divided by n minus 1, divided by n minus 1. This estimate the variance the smallest. So this is best. But how to prove this, or how to prove is this square is MVUE? So this is also a tough question. So we let's see, if we have time, we will check this. Maybe this one is that's it. So what we want is just to try to prove this sigma is squared unbiased. We need proof. We need to show thus like E is square equal sigma square. So this is unbiased, but E says sigma square thus not equal sigma square. So we can say this like the estimate from ME and MLE is biased. So this is so unbiased. This is bad. And so why this is, so we also claim this is MVUE, unbiased but minimize the variance. So how can you see, how can you show that? So this actually is also a tough question. Like here, if we wanted to prove this, so we need, let's say, we need to know the distribution force is square. So we need to know the distribution of or density function of is square. Okay. Okay. So this maybe will be our next class topic. So we use the next video maybe to explain this. Okay. So we can stop here. So thank you for watching.